on approximating the smallest enclosing Bregman balls. This is a joint research work by Frank Nielsen from Sony Computer Science Laboratories and Richard Nock from the University of Antilles-Guyane. Given a dataset S, we are asked to compute a simplified description called the center that fits well S. Depending on the optimization criteria, there are two ways to define the center. The mean average center is a point that minimizes the average distortion, and the min max center is a point that minimizes the maximal distortion. Those problems have been well investigated in applied mathematics. In computational geometry, the usual distortion measure is the geometric distance. The circumcenter is defined as a point that minimizes the maximum distance to the dataset. The centroid is defined as a point that minimizes the average square distances to the point set. And the so-called Fermat-Weber point is defined as a point that minimizes the average Euclidean distance to the point set. The drawings below depict the centroid, the circumcenter, and the Fermat-Weber point for the same dataset. In 2002, Badoiu and Clarkson presented an approximation algorithm for finding the circumcenter. A point C is said to be an epsilon approximation if it is within relative distance epsilon to the real circumcenter. Their iterative algorithm proceeds iteratively by finding a furthest point and updating a circumcenter as described below. We describe the iterations of their algorithm on this sample dataset. After the first 10 iterations, we visualize the ball traces and the core set, that is the set of points that has been detected as being the furthest point at some iteration. It is noticeable that the core set size is independent of the dimension d, but only depends on 1 over epsilon. Let us now define Bregman divergences, the usual distortion measure in machine learning. Bregman divergences are parameterized families of distortion. First, let us define a function f from a domain X to the real set R, such that f is strictly convex and differentiable on the interior of X for a convex domain X. Then the Bregman divergence df of x and y is defined as f of x minus f of y minus x minus y, the dot product of the gradient operator on f at y. Here we visualize f and its divergence df. As you can see, df can be seen as a tail of a Taylor expansion of a function f. Depending on whether we put the circumcenter on the first position or the second position on the divergence df, we can define two Bregman balls. For the Euclidean ball, those two balls are identical. It can be shown that the smallest enclosing Bregman ball is unique. Moreover, a recent theorem shows that the minimum average center for Bregman divergences is the centroid, whatever is the Bregman divergence. We generalize the seminal algorithm of Badoiu and Clarkson to Bregman divergences. It is noticeable that for square Euclidean distance, our BBC approximation algorithm becomes the original BC algorithm. The algorithm proceeds iteratively by finding the furthest points with respect to some divergence df and to update the circumcenter as described below. Let us now look at the first 10 iteration of our BBC approximation algorithm onto Itakura-Saito divergence. Here again, after the first 10 iteration, we visualize the sampling Bregman ball from which a distribution has been drawn and all the ball's traces along the iterations as well as the core set. Let us now look at another divergence, the Kullback-Leibler divergence and its enclosing ball. Again, we visualize the sampling Bregman ball, all the iteration of the enclosing balls, and the core set. Finally, let us look at several enclosing Bregman balls for the same dataset that has been drawn from a 2D Gaussian distribution. On the left is a square Euclidean divergence, on the middle is a Itakura-Saito divergence, and the right-hand side is a Kullback-Labra divergence. We have performed empirical convergence rate study that shows that the convergence of our BBC approximation algorithm is well under the theoretical bound of 1/t. We have shown that there is a one-to-one bijection between the family of Bregman divergences and functional averages. This is related also to some theorem on Bregman divergences and family of exponential distributions. Here are the main references to our research work. Finally, we would like to present our web pages where you can find more information and related materials. There's also some command line executable for creating the drawings that we have shown in this demonstration. Thank you.